physics-informed transfer learning for process control. And we'll go through each part of that riddle in just a minute. Here's a quick overview of what I'd like to convey today, make a small introduction for the benefit of the general audience. Then we'll dive into the first part of the research, some observations on how transfer learning can be used for model control. Then the core of the research, which is the general framework that we proposed as a method to the physics-informed transfer learning, and then an application to thickener control, which is a unit operation very relevant to the mining industry, and then obviously some conclusions and future areas of research. So again, as an introduction to the general audience, we want to start like from the beginning, right? Create the context where this dissertation takes place. And I want to start talking about models. This is one of my favorite quotes from one of my favorite books by Donella Meadows. Everything you know and everything everyone knows is only a model. We're going to talk about models today. Models are simplified representations of systems around us, and we're very good at creating models. The scientific community has models for pretty much everything, from the growth and decline of population of certain species to more complex phenomena like the supply and demand of a globalized world, and obviously the ones that this department is interested in, chemical processes, processes that generate certain product, and we use models to understand all of this and to control it as well. Universal model in chemical engineering and in many systems for that matter is this of a system that changes its behavior over time. And at any given time, we can look at the state of that system. In the case of chemical engineering, it could be temperature, pressure, concentration. We can look at the perceived state, and there's usually a goal, right? There's usually a certain temperature, a certain pressure that we're trying to achieve. Well, learning about this discrepancy, having a good model of how this happens helps us influence or control the inflows and outflows, right? This is the bread and butter of chemical engineering. It's inputs and outputs, and we can model pretty much anything with this framework. Now, when we know the model, we can control the process. And there's essentially two main categories. It can be a reactive control or it can be a predictive control. The better understanding we have of the model, the better chance we have of using a predictive control. The state of the art in industry in terms of predictive control is model predictive control. But the majority of the applications are actually a reactive control because it's much easier to implement. There are big challenges in trying to implement model predictive control because there are big challenges in creating these models to explain complex systems. This dissertation focuses on model predictive control and the models that we use to improve the performance or simply advance that field in a specific area. So speaking of modeling systems, there's essentially three categories. There's the first principles modeling, where you have to come up with the equations, the physical laws that describe the phenomena. They can be very complex, and sometimes we don't even understand the actual equations. One of my favorite examples is the Maillard reaction. That reaction, when you're toasting bread, it's like a page-long equation, and it's still not very well understood, right? So some of these processes are just very hard to understand. On the other side of the spectrum, we have the data-driven models, where you don't need to really use knowledge about the physical laws that govern that process. You just based it on observations, and then you use a statistical model to create a regression and kind of have a model of the phenomena without really considering the physics of it. And then somewhere in between is the hybrid models. And hybrid models enjoy the benefits of both approaches. And because they do combine strengths, you don't need a very sophisticated data-driven model, or you don't need a very complete understanding of the physical laws. So this is a pretty good spot, right? You can combine the best of both worlds and still have a good model, but they also suffer from the same shortcomings as the other two approaches, right? You still need data for the hybrid approach, and you still need some understanding of the process. This dissertation, again, focuses on hybrid models. And the state of the art right now in hybrid models is what we call physics-informed neural networks. Somewhat recently, 2019, this breakthrough paper by Arce at the University of Brown University, sorry, it came up with this idea of embedding some physical constraints in a neural network, right? Like, yeah, neural networks are great, they're amazing, but there's this problem of where's the physics aspect of it, right? I don't feel very comfortable extrapolating a neural network because I don't know where it's going to go. It doesn't know anything about the process. So they decide to use some physical equations as part of this optimization process of the neural network, and the results are amazing, right? They come with some partial differential equations that are very difficult to model, and the results are very accurate, right? So this is highly efficient when you have incomplete data, you have very small amounts of data, you kind of solve this problem of the hybrid modeling. It works in both directions. You can make predictions or you can estimate parameters, and it's computationally inexpensive, meaning you can solve it way faster with less resources than some of the big, deep neural networks, right? So that overall goes to better generalization. This is the state of the art, and this is where we start this research, right? Going off of these physics-informed neural networks. Now, physics-informed neural networks have two parts. The physics part of it is very specific to the process in question, but the data-driven part of it is, there's some flexibility there. You can use a neural network, you can use another statistical model. The neural network can be deep, can be shallow. And the state of the art in neural networks is what we call transformers. And they're also the state of the art already in process control applications, time-dependent applications. This is an example of a paper just from last year, 2023, people already using transformers to simulate complex processes like batch crystallization of dextrose. What I noticed, though, in this paper and a few others is that it's very specific, right? We have physics-informed neural networks and we have transformers, and we start using them in very specific applications, but we haven't taken a step back and looking at overall picture, right? Like, how do we use transformers? How do they come? So some general aspects of using transformers and physics-informed neural networks. But transformers are by all means better models, right? These are the models that are used in the latest wave of AI success. ChatGPT uses transformers. All these latest and greatest, they use transformers. And the main characteristic, what makes them so special, is that they can generalize better because they can look at the whole picture in a way, right? They are much better at long-range dependencies. So this is amazing for time series, for time-dependent processes like the ones we find in chemical engineering, because we can feed months or years of data, and it will very efficiently look at patterns through the whole spectrum compared to other networks like LSTMs or convolutional networks that are optimized for different purposes. Now, I'm going to make a quick parenthesis here. Transformers are also really good for transfer learning. This is the central part of the dissertation. What is transfer learning? I came across this paper in 2016 while I was taking a computer science class, kind of exploring my life options. And then I found this paper very interesting, right? These people were almost playing around, really. And they have this image here on the left of houses. And then they ask this question: can we transfer to the image on the left, can we transfer some aspects of a different object? And what will happen if we do that, right? So they come up with this paper. They feed a neural network with two data sets that are somewhat unrelated. On the left, you have these houses, this painting on houses. On the right, you have this other painting. And then the neural network kind of competes to create a result, and this is the result. It's kind of cool, right? Like we can combine approaches. It maintains the behavior of the source system, and it applies it to a target system. And the first thing that came to my mind is I have a lot of chemical processes that I wish would look like this, but they look like that. Can I transfer some of this magically to the other process and somewhat improve the performance, the control of that process. So I started experimenting a little bit with that. And I learned that there's actually not a lot of people working on this. The amount of people that are working on transfer learning applied to process control, to system identification, is just beginning to boom, right? Interestingly enough, 2016, the same year that style transfer paper was published, things kind of took off from there and people started asking these questions. 2023 was a record year in publications in this topic, and that's exactly when we published our first paper in the field. We published this in January. Some big names in the field, like Professor Christofidis at UCLA, they actually cited our paper later that year in a very similar application, right? So it seems like we joined this research at the right time. Like we're joining a community that's interested in this phenomenon. There are some publications, again, from 2023. This is a good example. But they go back to some of the previous problems, right? They're very case specific. Like, hey, look, here's how we can use transfer learning and physics-informed neural networks for a very specific case. And if you tweak the network in this very specific way, and if you move your parameters in this very specific fashion, you get really good results. And that's great, but we wanted to take a step back and look at it overall, right? How is transfer learning happening? Does it improve the performance of a control? Does it improve performance in the control of a chemical process overall, or is it just these niche applications where it can happen? Another thing that these papers were not considering was the data quality or the feature engineering. Again, because they were using data from the same process, right? And in the previous paper, where it was all about was it dextrose processing? Well, it was all data in that field, right? We wanted it to look more like this, a completely unrelated process. Can we learn anything from another process? And this is kind of where this industrial experience kind of comes into play. This is analogous to a very skilled operator from maybe the water treatment industry coming into the mining industry. It's a challenge that we see every day in our line of work. Well, this person has certain experience in this field. He can transfer that experience to this activity, right? So that we should be able to do that in this context of machine learning as well, transferring information from a related process, but not necessarily a related field. And that's something that these papers were missing, right? Exploiting the data from other domains. And finally, even, as of last year, people are still using some of the not optimal architectures like recurrent neural networks when we could be using transformers are much better at capturing these long-range dependencies. Now, in terms of Thickener control, the mining industry, well, there's even a bigger gap, right? Very few papers on data-driven approaches to begin with. A few instances of the neural networks actually being used for control, either surrogate control or to model the process for model predictive control. And for sure, no publications on transfer learning and physics-informed neural networks, right? So this is a very niche field of study where we haven't seen any publication. So this study is one of the first ones in that area, kind of advancing the mineral processing industry to the edge of these technologies. So to summarize the remaining challenges, another great paper that I used as the foundation for this work is by Professor Arthur Sweetman from University of Delphi, UT. In 2021, makes a really great review of where machine learning stands for chemical engineering. And I decided to take this as a framework and say, these are the two areas where I'm going to make a contribution, right? Introducing and enforcing physics and the problem of information and knowledge representation. Introducing and enforcing physics, we talked about it just a few minutes ago, right? These data-driven models are a little blind because they use only observations. We don't know if the outcome, the prediction, is going to fall within the physical limits of the process. Physics-informed neural networks solve this problem in a way, but they still require data. And there's some instances when that data is still very limited, like startup or shutdown. Again, this is where that industry collaboration comes in. Our line of work is always startup or shutdown, and there's no data to go with to make some predictions. Not only that, but there are other sources of data that are not being utilized, and this is the information and knowledge representation part. What about operator logs? What about standard operating procedures? What about operating original manufacturer manuals, original equipment manuals? All this could be used, but we're limiting to the time series information that we have available. Even with the use of physics-informed neural networks, there's still no general method for transfer learning. Again, transfer learning is, in the publications so far, it's limited to very specific case studies. We wanted to make a general framework. And then finally, we wanted to move across domains, right? What happens if we took data from a different industry, from a different process, will it still work? So as a summary of innovations, the things that we did to address these challenges is, number one, we present a novel use of transformers and physics-informed neural networks and transfer learning, the three state-of-the-art techniques for the well-known problems of system identification and subsequent model predictive control, and also approximate model predictive control, right? We can use these three tools to model the process itself or the control of the process. And we have some really interesting results. Second thing we do in this dissertation, I present in this dissertation, is we quantify the control accuracy improvement using these three techniques, the transformers, the physics-informed neural networks, and the transfer learning. We're able to quantify this in a more general way, right? We use a very, very simple model so that the intricacies of the process are not, making any noise, and we can answer in a general way the question, does it actually work? And finally, we apply this to a first study of its kind on thickener control for improved model predictive control. So this was the first question that kind of inspired the journey, and this was our first publication. Can we use transfer learning to develop an approximate control policy? We're not modeling the process itself, but the control for a specific target system using data from a different domain. And that was the first question. I was very intrigued by the observations on the experiments I was running. I was like, does it actually work? So we took two completely different systems. On the left, you have a level control, right? This is a simulated level control. These are the actual equations of two tanks, and then there's a pump and there's a valve that are used to manipulate the inputs to the tanks. And then we have an actual physical temperature control system, right? Something we can plug into the computer and we can plug into an outlet, and through a program, an embedded hardware, you can control the power output and control the temperature, right? Obviously, different domains. One of them is to level, controlling the level of the two tanks, and the other one is controlling the temperature. It's like, well, let's put it to test, right? Does it work? If I am an operator and I know how to maintain the level of two tanks kind of accurately, can I transfer that knowledge to a new application, which is now temperature? They're very different. Temperature applications have much larger delays usually than level. So it's not a straightforward task, even though they're kind of similar. So the first experiment, okay, let's take data from the source system, the two tanks. And we're going to take tons of data, 50,000 data points. We're going to create this abstraction where we kind of separate the physical process, because we're not interested in the process, we're interested in the control of the process. So we create this abstraction through feature engineering where we select only the height in terms of percentage. Our set point is the goal of level that we want to hit. And then the error is kind of a composite of the two, right? We fit this to a long short-term memory neural network. We train that network, and that's it. Right? The network is trained to control the levels of the two tanks. Then, almost like a brain transplant, right? Brain implant, we take that neural network trained on level control data, and we deploy it in the temperature control lab. Right? Like just completely naive. Let's see what happens. Experiment number 2, it's the same thing, but before we do this, with this brain implant, before we deploy it, we do a little bit of retraining of the neural network, just a tiny bit. And we use some data from the temperature control unit, 600 data points. And then that prediction we deploy to the temperature control lab. And then the last experiment, just for kicks, what happens if there's no training at all, right? There's no transfer learning at all. Maybe we're overthinking this thing. Maybe, we can do it without the knowledge from the two levels. So here's the results. Experiment number 1, just pure transplant, right? Like let's see if it is. Well, you can see it's trying, right? It's really trying to hit the set point, but it's kind of struggling at the same time. To put a number to it, the mean squared error, 138. Experiment number 2, if we do some retraining, here's where interesting things start to happen. You can see some behavior here. You can see the response kind of smooths out, and it actually hits the set point in a few of these instances. So that, of course, got us excited. But then there's also this experiment. If you don't do any transfer at all, well, the performance is actually about the same. So that's the question, right? Like, is it worth going through the transfer learning? Did we learn anything about this? Well, yes, we learned 2 things. Number 1, remember that this has only 600 data. Sorry, this is retrained with only 600 data points. And to achieve the same results without transfer learning, you would need about 4 times more data. So in a way, it solves that problem, right? You can transfer data from a different domain and reduce your data demands. So that's achievement number 1. Achievement number 2, yes, the mean squared error is about the same, but it's a little misleading because if I look at the 2 graphs, there are instances where this actually performs a little bit better, like right here in the middle. And something that we kind of inadvertently did, we found out after the fact, is that the data from the source system had a wider distribution of set points, while the data from the source system, because it was only 600 points, was very narrow. In other words, the set point changes in this system, in the target system, never went past 50%. But in the source system, we had set points everywhere from 20, 30, 80%. And somehow it looks like it's trying to extrapolate, and it does a little bit better job extrapolating outside the target domain. All right, so those were the 2 interesting observations. Like, we're onto something here, but of course it's a very specific study, and we can't tell for sure that this works 100% of the time, right? The other problem is that this is a long short-term memory network. It doesn't have the same capabilities as a transformer. So for all we know, it could have been an accident as well, right? But there's something there, the behavior is real, and we did this several times, so it's repeatable. There's definitely something there. Conclusion, can we transfer from 2 different domains, similar task, which is the control of 2 set points, but from 2 different domains? Yes, we can. Number 2, does it require the same amount of data? Well, it requires less data, 63% less data, and that's a win. Lessons learned, we're focusing on reducing the amount of training data, just like all the other papers. So we didn't look at the quality of the data. There's obviously some information from the target system that is not helping at all right? Like right here, maybe there's some information that's what we call negative learning. Maybe it's learning too much from the source system in a way that it's negatively affecting the learning. So the quality of the data was not considered. We should consider that. And also we noticed that there's a certain potential to transfer knowledge and increase the capabilities of the model to extrapolate. So we moved on to the next set of questions, right? Now we had a lot of questions. Okay, how can we control the how can we control the quality of the data? Now let's be a little more selective in the data that we transfer. Number two, how can we actually guide the knowledge? Remember that in this previous paper, it was really just plug and play and see if it was going to work. Now we want to be smart about it and regularize, guide the transfer. Next, can we quantify the performance? Can we actually say if it works or not? Can we put it all in a kind of framework or process to make it more repeatable? And while we're at it, we also apply this to modeling the process itself and not just the controller. So a lot of questions, but we with a lot of excitement. And this inspired the second paper, which was submitted in late August, and it was accepted for publication just a couple of weeks ago. Well, actually last week. So here's what we came up with, right? A 7-step framework, a 7-step process to do physics-informed transfer learning using transformers. Step number 1 is pretty simple. We define the source and target domain and tasks, like in any transfer learning application. Step 2, here's an addition. We want to identify what to transfer. We want to be a little more smart about the things that we are going to transfer. Number 3, typical of any transfer learning approach, you need to select a method. Number 4, we're going to adapt that method. Here's where the physics-informed part of it comes into place. We're going to add something to guide the learning. We're going to control the learning, not just blindly use it. And then the rest of it is typical machine learning process, right? You need to develop, train the model, evaluate the model, and maybe fine-tune it as needed. The source system is the most simple system you can think of, a first-order system with only 2 parameters to change. And the reason for this is so that we can see in a more clear way if the transfer learning is doing anything. I feel like I observed it with other approaches, complex systems, you have so many variables that sometimes you can't really tell, well, did this happen because of transfer learning, or did it happen because one of the many variables that are nonlinear and kind of take over the dynamics of the process. The target system is the same, another first-order system, but we're doing an actual design of experiment here with the 2 parameters, k and tau, ranging from 0 to 5. Like you said earlier, we were asking the questions, what to transfer. That was pretty obvious. We wanted to transfer the whole model. How to transfer, we decided to do it with some fine-tuning techniques. But we didn't talk about when to transfer. Is it even a good idea? Before we go through the whole effort, can we quantify if it's worth even trying? So that's where we run this experiment first. As part of the framework, before you move any further, first you need to identify what you're going to transfer. If you compare the source model, the first order model where k equals 1 and tau equals 1, once again, tens of thousands of data. You compare that against the small chunks of data of the 25 target models, and you see some patterns, right? Not as intuitive as you would think. The systems where tau is high and k is low are very similar to those where k equals 1 and tau equals 1. The systems where k is high and tau is low are further apart, right? So this is where we expect transfer learning not to work as well. So, if you need to make a decision, should I do it? Well, is it in the domain where it makes sense to do it? Or even better, can we only select data that's within this space? And that's what we did, right? Rather than saying, okay, well, it's not a good idea to go in this direction. No, maybe let's just select, using the same technique called dynamic time warping, modifying the algorithm a little bit, you can actually select the sequences that match the best. This is kind of an aggregate number in general across the whole time series. That's the score of the fitness, of the similarity. But there are some parts of the time series that are actually very similar. Let's extract those sequences and use them for training. So that's what we did with dynamic time warping. This is the target data. How similar is it to this? Well, it's similar here, but not here. And then it's similar again here. And only those chunks of data we're going to use, right? We're going to be very selective. Then we actually do the training, we do the transfer, and here's where we use our physics-informed architecture to guide the learning. We have two tasks here. In the system identification task, well, we can use the actual model, right? Very simple. In the approximate control part, not as simple because there's no physical equivalent, right? And when I tried to do it, I felt dumb about it. I was putting an optimization subroutine inside a bigger optimization routine, which obviously made no sense because I was solving the actual MPC problem within the neural network. So what we did is, well, what would this look like in real life? Let's say that there's no state-of-the-art controller, but there's a very skilled operator. He is my MPC. How would I capture his knowledge? Through a regression, right? Through a linear regression, maybe. That's what we did. This is just an autoregressive linear approximation of an actual MPC. Again, the idea here is to solve that problem of knowledge representation. We're building an approximate MPC with a linear term that's supposed to smooth out the response, but that term could very well be from operator data or from an approximation of how you think the process is going to work. Could be anything, right? You can get creative as long as it has the response that you want, which is tight control of the process. And these are the results. If you only use, I guess before that, parentheses, we run 3 different experiments, right? This is kind of the base case. If we don't use transfer learning at all, we just train with the data that we have. It's not a lot, but we use it. If we use transfer learning with no physics informed, with no regularization, just a little bit of retraining, and if we use a regularization. I mean, here's where we start to see some cool patterns. Overall, transfer learning does help, but when you embed some knowledge about the domain, in this case, through the physics informed, it really smooths out the response, right? But now we need to zoom out and say, okay, what does that look like in general? Can we see some general patterns, across the 25 target systems? And this is, again, some pretty cool results. If you only use the transformers, again, you start losing the battle up at that challenging region, right, of high values of K, like we expected. But if you use transfer learning, you can actually mitigate that quite a bit. That's because the source system has is a lot more variant rich. And this helps a lot, the data-driven part of things. And then if you add the physics-informed part of it, it obviously reduces it a bit more. But this was very interesting to see, that even without the pin, you can improve quite a bit using transfer learning alone. This is in the case of system identification. Then we also measured the extrapolation capabilities, similar pattern. Approximate MPC, different pattern, different results, but similar pattern. Once again, the physics-informed part of it really smooths out the response. And if you extrapolate, same thing, right? This is a very weird experiment at this point. I mean, we're trying to extrapolate to a domain that we've never trained on and that we've never seen. But the physics informed the physics component of it, which is as we discussed, is not necessarily physics, it's just a regression. It's actually smoothing out the process quite a bit. So yeah, that was very exciting. And this is the core of the dissertation is the quality of the data is not always a determining factor, but it's important. You know, that subsequence selection actually helps. In the case of the approximate MPC, that didn't help. But so again, the transfer and the regularization methods are also important. Some fine-tuning might be required in other applications, right? We know that. Another important thing from here is we didn't do any fine-tuning per target case, right? It's not like we went to each target and kind of fine-tune it. All target data were treated the same, and it was the same model across all of them. So that helps us quantify, you know, kind of observe a pattern in a general way, at least in this domain of tau and k being between 0 and 5. So of course, that's some exciting news. Now the real question or the challenge is, can we apply this to a more complex system? This was a very simple system. Is it going to work in a more challenging environment? What better way to do it than Thickener units? I've seen this many times in my life, and I've actually had to fine-tune some of them many times in my life, and it's a pain. It's very challenging. These are very challenging things to control, highly nonlinear water, liquid-solid separation units, and what makes them challenging is the disturbances. The feed coming in changes concentration quite a bit. Again, it's highly nonlinear. It's present in pretty much every mineral processing plant, gold, copper, whatever it is. Because it's your water recovery units. All the water that in a mining facilities, think of Kennecott, they have tons of this, and all the water that doesn't get recycled from here, all the water that's not clean enough to discharge from here, it goes to tailings. Well, the water that you can recycle from here, you can recycle right away. The water that goes to tailings is going to have to wait years to be recycled. It has a lot of impact, environmentally speaking. But it's very sensitive, again, to disturbances such as the feed concentration. And the equations to model are very hard as well. It was a fun trip back to all the transport phenomena classes, and it's just very hard to model, all right? You have a partial differential equation. You need to solve this in the two-dimensional space for it to make sense. This is kind of how it works. You have your feed here. This is the clarification zone where you expect your concentration to be near 0, your concentration of obviously solids, right? Tailings and other contaminants. Then this thickening zone, this is actually a simplification, but there's several layers. You have your dispersion zone, and then things start to settle. And then after a certain point, things start to compress. And then that compression has effects of its own. And because it happens at a very specific concentration, it becomes kind of a discontinuous function, right? So before the critical point and after the critical point, it's two different sets of equations, two different dynamics. That makes it challenging to model. That makes it challenging to solve. But it's important it's an important process in the mineral processing industry. So anyway, that's the model that I simulated in Python. This is not a real thickener. It's a simulated model in Python. But once again, the results are very similar to the previous case. When you use the transfer learning and physics informed, this is your result, the green line. Nice tight control to the set point. If you don't use the physics informed, it's still good, but not as good. And if you only train with the small amount of data that you have, not as good. Similar thing, we tested this across a different big range of scenario. This is our nominal condition, 0.13, 13% solids going in the feed, and then plus minus 20%. Now, here's some interesting things, right? At these concentrations, even the physics informed kind of struggles. So like, well, why is it happening? Well, in this case, it's probably a result of the nonlinear aspect of this system, right? It's just very nonlinear. The equations behave very differently at different concentrations, feed concentration values. But here's where the framework comes into place, right? Can we fine tune it? If we fine tune it, can we achieve a good response, or is it just a lost case? And I guess it's a hidden slide. I can show it in a minute, but you fine tune it just a tiny bit, your control horizon, and it's back to good performance, right? But this is one way to see it. A different way to see it, if you aggregate all the responses across time, again, zooming out, looking at the whole picture, different ranges of disturbance, it's still in overall a much better approach. The aggregate performance, the aggregate error is lower overall with physics-informed neural network. So that's, it's kind of the end of the research. And now the question is, what else can we do with this? What are other sources that we can use to guide the learning? Like you said, there's tons of manuals, operator logs, even images. What results could we see if we use generative networks? These are the type of networks that we use in ChatGPT, where you can put in a text prompt and receive an image in response. Now we're playing with the data formats. And can we extend this framework to other applications, right? Outside of mining, what else is out there? Conclusion, there were some initial observations and a proof of concept using 2 different domains. We were able to develop a framework around it, quantify the actual performance, and answer the question, does it work? In general terms, the answer is yes. We should be excited about that. And we demonstrated the use of transfer learning in a highly complex nonlinear system. As far as future work, here's some of the exciting things that we can do with transfer learning is we can extend it to other domains. This was process control, but there's also anomaly detection, process monitoring. These were all single input, single output processes, but we can extend it to multiple input, multiple output. This is one that I'm really curious to see, is incorporate additional sources. Again, we have operator logs, we have standard operating procedures, visual imagery, even audio. Right? SAG mills are controlled through audio. That maybe Professor Rogers knows more about it, but you actually have some microphones in the field, and depending on the noise is what you know about the model. And also explore new architectures, right? The latest and greatest in models like ChatGPT use what we call multi-source aggregative transformers, or MATs. And the advantage with this is that it uses transformers at its full potential. One of the advantages of transformers is that it's very effective with different types of data. It's not optimized just for images like convolutional neural networks. You can fit images, you can fit audio, you can fit time series, and it will process all of them very nicely, large amounts of them. So you can play with the sources. You can train your neural network with, again, pictures and time series and find patterns across both of them. And I think that's really cool. Finally, summary of the publications. First publication, deep transfer learning for approximate MPC was in January of 2023 in MDPI processes. Second publication, physics-informed transfer learning for process control, just accepted last week in industrial and engineering chemistry research. The last part, Thickener modeling and control, has not been submitted. It's pretty much sitting there in my Overleaf account waiting to be submitted. I'd like to work with you, Professor Rogers, maybe think of a good venue we can publish this paper, but out of the 3, this is the one that I actually think is, there are not a lot of papers. In fact, there's no papers at all in that area, so it's a good one. I've enjoyed collaborating with extremely amazing and smart people, and I've co-authored some other papers with them, including one where I was first author as part of my master thesis, which we can talk about later, was all about flying drones and optimizing view planning algorithms. Well, that went very long. I'm sorry, I took a lot of time.
Let's give a round of applause.